The camera is facing class right now, right? Where do you see? Okay, okay.
Yep.
It's not bad. It's good, but
I only see 3 people in attendance.
Yes, we have a record attendance today. It's a champion day. Maybe I should just give credit to those who show up in class.
Oh. I was the first one logged in.
Okay. 75% of credit.
Okay.
So, and I do have some printouts for everyone, like 11 copies, but I'm not sure if... Oh, probably will be a few people more. I see some motion through the door. Good. Hey guys, you're breaking statistics. I thought it will be record attendance of fewest number of people, but with you, probably not.
There's one more.
Huh?
There's one more coming.
I saw the camera from the last time we had Thursday.
Apparently a couple years ago in the physics department, no one showed up to computational physics one day.
Uh-huh.
And it turned out to be the professor's birthday that day.
Oh,
Oh my.
I do not have feedback, but I think the camera shows on the big screen. Do you see it, everything, or you need to adjust left, right, or zoom in, zoom out?
I just see where you're standing in front of the screen.
Do you see the rest of the screen itself?
Yep.
Oh, okay. Very good, very good. Okay, I think we are ready to start. So, I think you are always bored during the weekend and you do not know what to do, right? So you are suffering without homework. At least it is my little perception. So I'll send the copies through the email as well.
Thank you.
And this time there are no detailed step-by-step instructions, but if you vote and suggest that you need them, I will be happy to write one. And probably I will complete the homework myself to develop a grading thing.
When would the homework be due?
Tuesday.
Okay.
So the question number 1 will be to fill a chart, and if you will be sitting and listening what I'm mumbling today, it will be sufficient to fill this chart. But do not submit it today. Keep it, even if you fill it right now, keep it until Tuesday. And you guys have broken the statistics. I thought it would be under-visited class.
You sound disappointed.
Yeah, I'm so disappointed. It's just to cheer up your weekend. And here I'm showing my respect to copyrights of the published books. So if you do not trust to the mumbling of instructor, you can compare it with what is written. And basically, I will go over half page of this printout with details. Not the first half page, not the half page that is with big text, but somewhere in between. Okay, slide advancer. selected. Slide advancer. Slide advancer does work. Okay. So we are here on the first Hornberg-Kohn theorem, and before we started new chapter, density functional theory. Right before the break, we went over observables, periodic solids, Koopman theorem, and last time we went through Thomas Fermi theory, which is like historical ancient analog of DFT for a crazy universe that doesn't have ions, only electrons, and these electrons do not attract to each other. And right now we need to go through two theorems, one per lecture. It is not needed. You can slip this lecture and next one. This subject was important in like late 60s, beginning 70s, 80s, when there was a lot of skeptical perception of density functional theory. People didn't believe that it is real, that it can. So it's strange that it gives correct results often, and people designed theorems that prove that DFT should give correct results. The main confusion was that there is wave function is not needed to get right observables. And it sounds very strange because all quantum mechanics is based on wave function. And I'm going to go over theorems that are part of the community knowledge. Yes?
Do you mean that you don't need the full wave function to get sufficiently accurate results, or that it's...
If you are not looking into ground state, if you're looking on the, if you're not looking to excite, if you're looking on ground state, all observables can be extracted from the density.
like exact, or...
Exact. If you know right functional. There is a theorem that correct, absolutely correct functional does exist, but it is our problem that we do not know it. But mathematically,
It's there somewhere?
yes, correct. But this idea that right now no one starts steering hairs away, no one tries to throw tomatoes at me because we are in 21st century. If I would declare it in like 70s, probably it will be very emotional reaction. So we will go over two theorems, and the most, on my opinion, the most important lecture of the whole course will be next week Thursday, Kohn-Sham algorithm. So it is the like cream of the cream. It is not complicated. It's really easy to perceive, but if you are aware of it, you are like independent researcher ready to jump in.
Will we also show the Kohn-Sham orbitals?
Oh yes.
Okay.
You can catch me in lying or formally contradictory things. Density functional theory is formulated. Theorems are formulated without wave functions, and there are exotic people who do orbital-free DFT without any wave function. But just for matter of comfort, there is a little admixture of orbitals into the procedure that we know as Kohn-Sham orbitals. But formally they are not needed. One can do everything without them. Okay. It's too early for us as a group. It's just from previous year, but one day you will select subjects for presentations. And later you will select subjects for the project. So this is the homework. Few boxes of the flowchart that I distributed. The compute absorption spectrum for this perovskite cluster. It should be easy, just repeat what we did in the lab. And then it gets more and more complicated. Compute absorption spectrum for the last thing we did in the lab, was the periodic nanowire of titanium dioxide. And do not hesitate to contact me. I will answer any questions and try to log in and give some suggestions. Then next, so up to here, I think everyone will do more or less comfortably. Then it gets more complicated. So prepare a three-dimensional structure of not cluster but bulk of the perovskite. And it will be too challenging to design everything from scratch. I will provide some input coordinates to start with. But your task will be to select these adjustments parameters when you create postcard. And surely make density of states and absorption spectrum. And for those who will still feel bored after this, one can do the same steps for lect18-Thu. Okay? I'll skim through very quickly because we went through this recall before. So we recently finished Hartree-Fock theory, right? And there were kinetic energies of electrons, attraction to ions, direct Coulomb and stabilizing exchange. Here is the flow chart for Hartree-Fock procedure that later on we will develop same, not the same, but very similar flow chart for the density functional theory. So all theories target the same thing, the total energy and several observables. I have invited you to sleep during the lecture. If you literally followed my recommendation, you may develop a little confusion between too many flowcharts. So there is a flowchart for the homework, which is just a logical stream for a proof of a theory. And there will be later a flowchart for how the algorithm works. There are two different flowcharts. Just do not mix them. Okay, and recently we covered observables. When we were doing it in this room before the break, it was kind of not quite necessary, but now after you are starting to compute absorption spectrum, it makes more sense, right? So the oscillating electric and magnetic field are the light, right? And through dipole approximations, they affect molecules and materials. So the energy of photons is absorbed by promoting electrons from occupied to unoccupied orbitals, right? And here is the dipole, which is just positive minus negative times distance. And there was an observation that formally the dipole interaction between light and matter should be processed as matrix element of overall dipole in the brine cat of Slater determinant, which is a disaster. And we were proving that it can be waived, it can be avoided through, so we didn't do formal proof, but we went through multi-electronic Hartree products on the left and right for ground and excited. We took the dipole operator and we followed the brine cat procedure. And as a result, carefully looking through this thing, we found that expression for matrix element in multi-electron basis can be reduced to matrix element in basis of one electron orbitals. So it is to some sort of an approximation, but very good and appetizing approximation. So what you are, we all are doing in the lab is that ability of a molecule or material to absorb light, which means promoting from ground state to excited state, which corresponds to jump from orbital I to orbital J, right? Can be correlated with matrix element of transition dipole between orbitals I and J, right? It is what we are doing. So orbital I, orbital J, matrix element of position operator. And here are the little wordings, what is what. When you will be doing research projects and written reports, it will be very relevant to put equation like this in your reports. Just give heads up. Periodic solids. Remember what we did last thing before you, when we all were tired, last thing before you departed from the lab. We took a little unit cell of this titanium dioxide and then assumed that there are replicas, and there is a little offset of distance between them, right? So it's standard thing for periodic materials, and then there is a block theorem for a special type of wave function. Okay. And you all remember Koopman's theorem that ionization and affinity are tightly related to energies of orbitals. Okay, we just studied density functional theory, where instead of wave function that gives you total energy and all observables, one can play with only density of all electrons, which is very appetizing because it is wave function has as many independent variables as many electrons times 3, right? And density has just 3 independent variables. So it's like many orders of magnitude cheaper procedure. We went through the Thomas Fermi theory, right? We split all space onto boxes and decided to express total energy of the universe as function of density, which is number of particles per box divided by volume of the box. And through a little exercise and recalling of your favorite equation from basic quantum theory, particle in the box, right? We went to I probably just approach and click the yes, it's much quicker. I still forgot, I do have a movie for this density of states, but now Gage and Ben are both here. They remember this movie. If you don't believe me, ask them. So how the shape of periodic or structure, not periodic, of nanostructure affects the density of states. Remember, there was a lab and movie in the basic quantum theory, PCAP, right?
I think so.
Okay, thank you for the support. And we use this occupation and density of states to find momenta, and here's the main result of the Thomas Fermi theory, that the energy, total energy of the universe that consists of many electrons, non-direct electrons, with density defined in each point of space, is just a three-dimensional integral of the density to the power 5/3 of this density, right? And it falls into definition of a function of a function. So if we do know density, we can find total energy, and this is symbolized by rectangular brackets. Okay, 5/3. Very soon you will see that so-called LDA, local density approximation, will use 4/3, which is relatively close. So it is not far from this, the simplest version of DFT. So functional is conversion of a function into a number. Example is when you, I have forgotten my pedagogical trick. I needed to erase it and invite one by one someone to write these equations on the board. Imagine that you are coming and writing it, okay? So if you're integrating wave function square, you get 1 for 1 electron. If you have n electrons, you get integrate density for each, and then you get n for number of electrons, right? And if you get total density into the power 5/3, you get total energy if there are no ions, and you use Thomas and Fermi. So L stands for function of a function. Okay, so a little of definition, and for today and next Tuesday we are going to speak about a little philosophical things they're not practical, and they are a little orthogonal to intuitive thinking. So just prepare, if you're not sleeping, which you're welcome to do. So just be prepared that there will be some counterintuitive things that are not immediate, not natural on the first glance. So when we all love and practice quantum mechanics, we already develop a mindset as like string, a pathway, a logical sequence. First we define Hamiltonian operator of energy, then we diagonalize it, and then we find energies or observables after we're getting wave function. So straight procedure. Hamiltonian is first, wave functions are second, energy is third. And at the point number 4, we may or may not find probability density or charge density, right? So it goes at the very bottom of the food chain, the density. It's like not the top. One thing. Another thing, what is included into Hamiltonian? If we refer back to the very beginning of the course. Of course, we have things related to nucleus and we have things related to electrons. So we focus only on electrons. We do have kinetic energy of electrons. We do have attraction of electrons to nucleus, and we have electron repulsion. So first and third, kinetic energy of electrons and repulsion do exist even in case our universe is missing ions, right? So imagine crazy dream of a physicist, opposite to chemist. Like there is a universe where there are no molecules, there are no ions, only electrons everywhere. So then in the Hamiltonian we are missing the second term, no attraction to nucleus. But fortunately or unfortunately, we are living in a world with molecules, where electrons are getting trapped by positively charged ions, right? So what determines property of a molecule? When you are doing practical computational chemistry work, to do homework or to do your project, or hypothetically to find descriptors for your cheminformatic models, you're building atomistic models, which means you're setting up Cartesian projections of each ion, and then you set up type of ion, right? Type of ion with number of with charge or whatever, right? So your input, the only input you do when you do practical work, is setting up positions of ions. The rest is inside your code. You do not change it, right? So the only thing that is foreign, outside, external to a molecule from a point of view of a computational chemistry theory is position of ions. Or if you speak more philosophically, potential, attractive potentials that ions exert on electrons. You see? So if you
based on their position.
Hmm?
You said the ions which interacting with electrons based on their position.
Each ion
Yep.
is positively charging, and therefore it attracts negatively charged electrons.
Yep.
And ion creates a Coulomb attractive field potential around. Each ion creates Coulombic field. Another ion creates another Coulombic field. And if you add them together, it will be potential exerted by all ions to electrons. Right? So you are setting up positions of ions, but for electrons feel overall potential of all ions together. And therefore they see, oh, in this area there are so many ions, they're so attractive, let me go there. Right? So here is a little counterintuitive thing. this nuclei to electron attraction, summation of Coulombic terms, is external. So the only thing this external is counterintuitive. So it is external potential, and external it is in the sense that for electrons, like we all brother electrons. Who is against these external ions, right? It's a little counterintuitive.
So you're saying the ions are the external portion of that?
Of the Hamiltonian,
Yeah.
of the world of electrons. Like if you have Thomas Fermi model, where like all electrons are living together, and suddenly something external comes, like ions. Okay.
So the V and E is our external part, and so our kinetic and our potential, that's going to be
Kinetic energy of electrons, and
so it's kind of the internal.
Kinetic energy of electrons and electron repulsion are internal. But
Okay.
attraction to ions-
Now we're making sense. Okay.
Okay, attraction to ions. So our lowercase is position of electron, our uppercase is position of ion.
So basically, you're just describing what's happening inside your system and outside your system in the Hamiltonian.
Well, it's all together.
All together,
I
okay.
warned you that it will be counterintuitive. It's all one thing, but we just philosophically split them onto parts.
Okay.
And this term, I apologize for spending too much time, but it will be important for the theorem that we are going through right now. So, let's play Wheel of Fortune. There is a word stupid, but it is like not very academic. Let's find polite way to say that an idea is ridiculous or stupid, a noun. And you already have first and last.
Can I just say it?
Absurd? Yes.
Oh, I'm sorry.
Well, the $1 million goes to Ben.
Oh.
You got it? So here is thesaurus synonyms. So absurd. Originally, well, Ben studied Latin, to my knowledge, and originally this word is Latin. So absurd means, you see, nonsense. So okay. I had a helper who did it for me and told that everyone in the audience will like it. So, here is the thing, the theorem that there is. If you are comfortable with this, you can either fall asleep or just lift and depart. We are going just to provide proofs for this little line. But it is very strange. Some years ago, community was strongly against it. And there are some echoes of this rejection of idea even these days. So if you tell, I'm doing ab initio computation, specifically DFT, some people may start throwing tomatoes at you, telling like, DFT is not ab initio. I'm just telling different opinions. So the first theorem of Kohn tells that if you do know the density of your electrons, and it is all philosophical, it's not procedure how to compute. It doesn't tell, like, suppose that you have completed some computation, or you have data set, and the knowledge of density determines external potential and determines total energy. So the basic idea of DFT, so that if you know, and you see, there is no wave function here completely. So if you know the spatial distribution of all electrons, it's much cheaper than wave function. Then you can reproduce which ions were staying at which place. you can reproduce external potential. And then and you can find total energy and basically all observables. So knowledge of density determines all knowledge about the system. This is quite challenging and inducing resistance in community. And this statement can be proved rigorously. And if you do not like what I'm talking, there is like chapters in the book that cover it.
So I have a question. So this is more or less when you say have a bulk system, and you're attaching
any system.
I'm just giving an example. So say you have a bulk system and you add some ligands. Are you more or less just kind of doing a surface calculation without going deep into...
These theorems did appear a lot ahead of time before any computational codes. So people proved the theorems before one was able to prove in practice.
Okay.
But if you want a practical example, I think we were plotting orbitals and ESP potentials, right? But we were not plotting total charge density, which was possible in with Gaussian, and we will do it for sure with our new chapter. So if you did a calculation, create a charge density distribution for all electrons, plot it, and then erase everything else on your computer, then this information about charge density distribution is sufficient to recognize and reproduce which ion at which position was originally placed.
I see. Okay.
Okay? And the proof of this theorem will be based on the mathematical trick. Ben, which trick? Why did we look for this? Ad absurdum. So we will assume that this statement is wrong. And then we will do some simple logical steps which will bring us to a nonsense.
Is that a proof by contradiction?
Proof by contradiction, yes. Good. It's a different terminology in each language. And it doesn't coincide in each one I practiced. So ad absurdum is original Latin, and in modern languages it's so contradiction. And in Russian it's like from adverse or from idiotic. Okay. So, if you would object this theorem even before proof and tell I do not believe it, how density can determine positions and of ions and external potential? Well, not as a proof, but just to make you more happy with your mind. We know that typically direction is opposite, right? So the positions of ions is a logical source, and density is consequence. I'm okay with this. So in forensics, what's a typical way if like there was a crime? What is the most typical way to recognize who was doing a crime? If there
Take the fingerprints.
Yes. So a criminal is a source, and density is a fingerprint. Okay? So by looking at a fingerprint, you can recognize who was present here. So density is a fingerprint of a molecule. Okay? Density, external potential. Good? So we are going to feel, well, I'll try my best, and then you'll do the same either now during weekend, and then I'll check maybe you'll do better than that. So we will start from one wrong thing, one good thing. We'll do some operations, and then we'll go to ridiculous contradiction. And we will assume that. So let me repeat once again how the theorem is formulated. The density determines total energy, absolute value of total energy, which is one and only one. This is formulation of theorem. And our wrong assumption that should lead us to a ridiculous contradiction is that there is more than one total energy coming out from one density. Which means like there are two criminals who leave the same fingerprints. Okay? And through some mathematical steps, or logical steps, we will prove that no, it will be ridiculous. Fingerprints are unique, even in the quantum world. So, on one side, we will assume that from one ground state density, we have two branches, two different external potentials, and two different total energies, like two branches. Here we will use knowledge, another theorem that we discussed before, the theorem that is behind Hartree-Fock theory, the variation of theory that we all are assumed to know in the middle of the night if we're woke up. Which means that variational principle is outside of DFT world. It exists on its own. And it tells that if you have Hamiltonian, you have ground state wave function, then you have one and only one ground state energy, and any change into wave function in respect to this ground state wave function will provide bigger matrix element of any other than ground state wave function, will provide energy bigger than ground state energy. So any change in wave function will provide increase in energy if your wave function is not a ground state wave function. So we take it as a piece of knowledge that we are relying on. So here, add something to wave function. So we will combine formation, hypothetical formation of two branches of external potentials and variational theorem. So we will blend them together, and I could keep a long intrigue until the end of the hour, but we all are adults. So here is the nonsense that we will arrive at. So energy, total energy of branch A plus total energy of branch B will be less than total energy of branch B plus total energy of branch A. So two equal things, and one will be less than another, if this hypothetical statement is correct.
So why is it nonsense? We'll get to that.
1 plus 2 is smaller than 2 plus 1. Is it normal, or it is a little nonsense? Well, for regular people, I don't care. I have my food, and I don't care who is bigger than what, right? But if it is someone who is dedicated with mathematical rigor, it's like against the rules. So it's nonsense.
Mm.
It should be equal, not smaller.
Right.
So here is the
okay, I see.
Contradiction. Absurd. And therefore, since this one is absurd, we will tell, it's a little hidden here, that one density gives only one external potential and one total energy. One and only one. Yes?
So, in that top left box, you have
Top left.
the density going, and then that's an arrow to the right for.
I was repeating. It is a redundant repetition of the same statement.
It's just.
Yeah, it's same rule. There is no logic behind it. I was just repeating it several times and making marks.
And then to the right of that one, that wrong assumption, is that a consequence of someone assuming that a density can't lead you to the coordinates? So
Yes, let's assume that one density can lead to two different external potentials, or two,
Okay.
that the same ground state density can be generated by two different molecules.
Okay.
Okay? Same thing, just with a little non-hand typing. So if we are living in the... Oh, skip this. I have a better slide. So let's consider these two branches. First, branch A. This branch A has external potential V sub A, Hamiltonian V sub A, because as soon as we find external potential, we can reconstruct the Hamiltonian, right? Because everything else is trivial. And then if we put here I need an empty slide and probably write from scratch. There is nothing wrong here, but a live writing is better. Here. So we do have branch A. Density A, external potential A, Hamiltonian H sub A, and ground state wave function sub A, and total energy E sub A. Right? So in this branch, we do have that E sub A equals psi A H A psi A, right? So there is no intrigue. We just follow standard things in a branch. Now, what if we borrow and in the branch B there will be row. Oh, no, it's same row in both branches. Same row, but it gives V sub B, H sub B, psi sub B, E total sub B. So now we are going to borrow the wave function, which is assumed to be ground state wave function for branch B, and we plug it into this expression for branch A. So we put psi sub B here and there. And we can, since we assumed that external potentials are different, then Hamiltonians are different, and these wave functions are different, right? And total energies are different. So we can write down that psi sub B is psi sub A plus some delta psi, right? And if we plug in this variation of the wave function into variational theorem, then psi a plus delta psi h a, psi a plus delta psi. How would it relate to ground state energy of the branch A? Like here, when it is its own ground state wave function, it is equal. But if we increase the wave function, what will be the sign here? Can we still put equal sign? Should it be bigger or smaller?
Bigger.
So what is bigger, energy or matrix element?
Matrix element.
Correct. Yes, matrix element is bigger. Okay? And we can interchangeably write the same expression, like swap the indices and write the same thing for branch B. But the idea that we follow two branches and then borrow wave function from one branch to another one. Okay? Object right now or stay mute forever? Okay. Now prepare for one more mathematical trick. I apologize that I do not write everything by finger from the beginning. It would be probably better for discussion, but if there are already slides, I do not feel comfortable discarding them. So, we had Hamiltonian A for branch A. We have our wave function for branch B, and we have this bigger sign, right? Or energy is less than matrix element. Now, mathematically, we are not forbidden to add and subtract the same thing, either number or vector or operator. So if it is operators, we minus HB plus HB, right? It's completely legitimate. We are not violating anything. Now let's process this difference of these two Hamiltonians and this HB part separately. So on this right side, first term in the right side of inequality, we have matrix element of the subtraction of Hamiltonian for branch A and branch B in the bracket of the wave function of branch B. And at the second term on the right side of inequality, we add together the matrix element of Hamiltonian of branch B in the ground state wave functions of branch B, which will be actually, by our definitions at the beginning of the theorem, will be ground state energy of branch B, right? Total energy. Again, think once again, develop any objections if you can, because it is almost, it is the last step when we are thinking, when we are doing creative thinking. The rest of the proof is just mechanical following of the like, very, very simple operations. So you didn't catch me, or you didn't catch original authors of theorem on anything wrong at this step. Okay? You didn't. Okay. So what I'm going to do, again, no intrigue, plain open card. Rewrite this expression by swapping A to B and B to A everywhere. Like if you started from opposite branch. And then adding together these two inequalities and see what happens. So just same thing as we did before with little better writing. And a little observation. So each of these Hamiltonians for branch A and branch B is composed as always from kinetic energy of electrons, electron repulsion, and external potential. This is correct for both branch A and branch B. And kinetic energy of electrons is the same in both branches. Electron repulsion is the same in both branches. The only difference in these Hamiltonians are external potentials. Okay? So if we subtract these two Hamiltonians, the result will be just subtraction of these two external potentials. Good? Like adding each column, H sub A minus H sub B, is just difference of external potential A and external potential B. So the expression that we started from is changed to the form where we have total energy of branch B, total energy of branch A, and here matrix element of the difference of the external potential of the branches as a matrix element of total energy of branch B. A little thing that seems, I would say it is natural, but if you were literally following my suggestions and sleeping, right now there is a good moment to wake up for a couple of seconds. So it will be not intellectually changing, but it will be something useful for the future and for writing methodology sections for your written reports and for speaking the language of DFT. So I'm going to go from red line to black line and share enthusiasm that they are equivalent. So if we are finding expectation value of an operator, especially if it is not differential operator but just diagonal operator, like Coulombic attraction, which has only diagonal term, then expectation value is, instead of Bryant cat, you can do integration. Wave function star, wave function without star, and the thing that we need to average, right? Good? Standard thing. But now, wave function star times wave function without star is nothing but density. If you follow in traditional interpretation of quantum mechanics, probability density, and if you are big supporter of density function theory, it's charge density. Okay? So, this matrix element formulated on a language of like canonical quantum mechanics can be without any tricks. It's completely smooth and rigorous transition. Can be reformulated on a language of integral of density times the thing that we need to average. Okay. No one objects. No one found it strange. It seems natural for you. Okay? Give me a sign if it is strange, but...
Are we, I mean, it's interesting. I mean, the red part where you have the wave functions and then it's just the one, whatever that's called, of sub B, right?
Wave function.
The wave function. So I guess I'm a little lost, maybe, on that part.
Well,
or maybe not.
We are mathematically expressing the same thing. Those two are equivalent, but they are kind of same thing expressed in different languages. This is language of wave functions, and this is language of densities. So
Okay,
if we do
okay.
know densities, we can find observables as well.
Okay,
By
got it.
performing
Okay.
appropriate integration. If you accepted this little change in the notation, then forget about this red thing. I just was lazy. Instead of writing 2 lines, I wrote 1. But originally, I'm converting this black line in everything black written here. So energy, total energy of branch A is smaller than this matrix element, which is not, according to our previous slide, it is density B sub B, which is just wave function B squared, times difference of external potential, A minus B. So this line is the same as this line, plus total energy of branch B. Okay? And no one forbids us to swap A to B or B to A consistently. If I would be more workaholic, I would make just a second line. So, what is good and what is bad in this expression? It is good that we are speaking on the language of density. We do not have wave functions anymore. We removed wave function from the consideration. It is good that we do not have any kinetic energy of electron and electron repulsion. And the bad thing that we are putting index rho sub B and rho sub A. No. We agreed that we have only one density. And whatever we have wave function psi sub B or psi sub A, after making absolute value squared, we should arrive to the same density. This is not discussed. It was our original assumption. So we should remove the index A or B and put just density here. Okay? And the rest of indices will stay. So there will be 2 inequalities. Okay. One day I remember I had a little energy to do something. So we do not need index here. So it is one branch, total energy of branch A, density of external potentials, overall density, less than. Or Kurt taught me caret. Or it is caret back. Is it same also caret, or how do you call it? Like if it is bigger, it is caret. If it is smaller,
Less than greater than something?
huh?
Less than greater than?
Okay. Nice. So energy less than matrix element. And here for another branch, branch B, total energy is smaller than matrix element of external potential differences with absolute total density here, plus energy of branch A. And it is what I've just told. There are no different densities in branches. Density is the same for both branches. So now we do need just to add together these 2 lines. If you are energetic and enthusiastic, you can do it before I walk to the keyboard and flip to the next slide. So when we add together left side of inequality, we will get E sub A plus E sub B, right? When you add together right side of inequality, you on the rightmost you will have E sub B plus E sub A, and here the density is the same. Here V sub A minus V sub A, V sub B minus V sub B. So they will cross cancel. this one will cancel this one will cancel this one, right? And you get E sub A plus E sub B smaller than E sub B plus E sub A, right? Which for rigorously thinking mathematician is absurd and ridiculous contradiction, which means that something at our original statements was wrong. Either variation of theorem was wrong, or assumption that one density can generate two different branches was wrong. Since we all are believing so much in variation of theorem, we are coming to conclusion that different branches is wrong. Okay? Canceling. So our original statement that same charge density leads to alternative branches of observables, no. It brings it to absurd, therefore we cross it out. And we start, since no one was objecting, we, through democratic procedure, no objection, it is assumed correct. That density determines external potential and total energy and all observables. First theorem of Kohn. He did 2 theorems and 1 algorithm and got Nobel Prize for it. So you are 30% away from Nobel Prize by now. Total charge density determines only one branch of observables. And here is your flowchart that you may feel to populate your time when you are bored during the weekend. So in our straight logic, the set of nuclei and their position determine chemical properties. And there is no doubt. But logically, just in a space of ideas, the electron density is a fingerprint that can reproduce ionic potential. And this idea that fingerprint allows to reconstruct ionic potential will be needed for the second theorem, and later on it will allow to set up algorithm and do all calculations so much quicker than anything else. So the second theorem will tell that there is only that correct functional does exist, and there is only one correct functional that allows to find total energy if you know density. Find energy if you know density. Done? I'll stay here to answer any questions, but there are no more materials. Please feel free to send multiple emails regarding homeworks. Do not waste time. I wouldn't say that the homework is super quick, but if you ask questions at the right time, you request help, either from me or from each other, it will be so much quicker. Do not sit and hit the wall if something doesn't work. It's so much quicker through collective intelligence of the whole group. Okay?
Awesome.
Very good. Have a nice weekend. I hope it will be not boring.
No. Yeah. All right. Thank you. Have a good night.
Thank you. You too.